moving on to our final topic of spontaneity here. The final state function that we are going to be working with is Gibbs free energy. What is Gibbs free energy? It's looking at something called delta G. Gibbs free energy, also known as delta G, has to deal with the overarching idea of the maximum work energy available to the surroundings by the system. And it's looking at spontaneity. We know from the second law of thermodynamics that states the delta S of the universe is equal to the delta S of the system plus the delta S of the surroundings. And that overall, for a spontaneous process, delta S, I'm going to write this on the side, for the universe has to be greater than 0. Just don't forget that, okay? Now, when we want to think about everything in terms of the system, we actually can derive a calculation that is specifically focused on the system supplying work energy to the surroundings. What we have to do is a little bit of algebra. Now, we do know that we can replace that delta S of the surroundings with the negative delta H of the system over temperature. So we do see that part of spontaneity is enthalpy and temperature dependency. Okay, now we want to get rid of that denominator T. So what we do is we multiply everything by negative T, all right, to get everything kind of normalized here. So negative T delta S of the universe is equal to negative T delta S of the system plus delta H of the system. Okay, that kind of cleans everything up a little bit more. Now, we do know that the negative T delta S of the universe here needs to still be greater than 0. And what we do is we normalize this and we say this is now called Gibbs free energy, delta G. And that is equal to, I'm going to put the negative at the end because that's typically how we write it, delta H minus T delta S. All right, and all of these are going to be geared towards the system. What is the change in energy of the system? What is the maximum work energy that can be released to the surroundings? If delta G is equal to negative T delta S of the universe, the same principles apply. We wanted delta S of the universe to be positive. That means overall delta G would have to be negative for a spontaneous reaction to occur. And that's what we're going to talk about next. A process will be spontaneous when delta G is negative. Under the following conditions, delta G will be negative. If delta H is negative and delta S is positive, these are both favorable. All right, both favorable conditions. We have an exothermic and a more random product. That means the reaction will be spontaneous. If delta H is negative, favorable, but delta S is also negative, unfavorable, delta S should be relatively small, negative, right? We want the more positive, the more favorable aspect, delta H, to be the value that is larger. And again, we can still see an endothermic reaction, but it has to accompany a large entropically favorable reaction. And then we'll talk about temperature in just a moment as well. Delta G will be positive under the following conditions. Obviously, if delta H is positive and delta S is negative, both of these are unfavorable. That means that the reaction will never be spontaneous. Never. You can never have an endothermic and a more ordered reaction, okay? If delta H is negative, but delta S is also negative, then we do see that a non-spontaneous reaction will occur if the delta S factor is larger. Again, if we are looking at what is favorable and unfavorable, to get a delta G to be spontaneous, we have to have bigger favorable aspects. To get delta G to be positive or non-spontaneous reaction, then the more unfavorable aspects will occur. Delta G is 0 at equilibrium. Remember, this was a reversible process. So we showed the derivation for Gibbs free energy. Let's just talk about what this definition is again. Delta G, or Gibbs free energy, is the maximum amount of work that can be released to a surroundings by a system. What we're trying to relate here is the amount of energy that could be released in a spontaneous reaction. Gibbs free energy is also called chemical potential because it's analogous to the storing of energy in a mechanical system. Because delta S of the universe determines whether the process is spontaneous, second law of thermodynamics, delta G also determines spontaneity. Now we do have a chart right here to understand the favorability, right? And what that means for spontaneity. We'll be working through all of these processes. Notice again, favorable and favorable, always spontaneous, right? Low temperatures and high temperatures, always spontaneous. Unfavorable, unfavorable, always non-spontaneous. It's the last two that we're going to spend some time in class working with when one aspect, enthalpy or entropy, is favorable and the other one is unfavorable. That's what we call a temperature-dependent reaction. It will depend on the temperature and the actual magnitudes of delta S and delta H to understand whether the reaction is spontaneous or not. It could be spontaneous, it could be non-spontaneous. We need more information. Now, let's go ahead and practice calculating these, okay? This is a good one to utilize because if we look at the delta H and the delta S, this is a temperature-dependent reaction. Why? Delta H for this reaction is positive. Delta S of the reaction is also positive. Delta H is unfavorable. It's endothermic. Delta S is favorable. It's positive. Entropy is increasing. Temperature dependent. All right. Let's calculate delta G at 25 degrees Celsius and see whether the reaction is spontaneous or not, okay? Again, because of the units of S, we need temperature to be in Kelvin, 298 K. Delta G is equal to delta H minus T delta S. We have a positive 95.7 kilojoules minus 298 K. Delta S is typically in joules, so be very, very careful with this math. If you're gonna keep delta H in kilojoules, you better convert delta S into kilojoules, or vice versa. You can go either way. Keeping it in kilojoules will then get us 53.3 kilojoules. Positive. All right, so what does this mean for answering the question of A? The reaction at 25 degrees Celsius is non-spontaneous. If the reaction is not spontaneous at 25 degrees, we're moving on to B. What temperature would the reaction become spontaneous? The best way to do this is to solve for temperature using the exact same equation, right? Using our same Delta G is equal to delta H minus T delta S, except for now we know 0 is the threshold. So let's plug in 0 for delta G and solve for T. Again, when we solve for it, it will be in Kelvin. Take a minute, solve for T. Do the algebra, rearrange. We should be getting 673 Kelvin. Very high temperatures. Why? Because notice, look at our equation. If delta S is the favorable aspect here, then we should see delta S, which is multiplied by T, be better if it's a larger value. So again, large temperatures, large entropy factor. This overall is the entropy factor here. All right, so if entropy is favorable, we want high temperatures to really buff up that factor so that it makes delta G more negative, right? More likely to be negative because again, we see that negative sign in front of the entropy factor, T delta S. If for some reason entropy is unfavorable, right? Just play devil's advocate. If entropy was unfavorable, we want that to be as small of a value as possible so that is more spontaneous at low temperatures. Yes, we have the ability to calculate delta G from standard states as well. We do have a table that tabulates delta Gs at standard states for reactants and products. And so we would say products minus reactants again, just like we've been doing for delta H and delta S. At temperatures other than 25 degrees, assuming that the change in enthalpy and entropy is negligible, we would use our equation that we just did. All right. Or you can also use a kind of Hess's law, right? Where we have multiple steps of overall delta G's tabulated. We can manipulate those reactions and delta G gets manipulated the same way as delta H. So overall, we could even do a pseudo Hess's law to find the overall delta G of a reaction. Extremely valuable, extremely helpful in determining the multiple ways to calculate delta G.